pirates' boats seafaring.
So we say and so we do.
There's none set sail with finer bearing.
Greetings and welcome to another exciting lecture in geomorphology. We're back again. We're shifting gears and moving on to another exciting topic, another really important process for thinking about the shape of the Earth and the landforms at the Earth's surface. That's right, we are going to be talking about glaciers and glacial geomorphology this week. So we'll separate our study of glaciers into three distinct lectures. Today we're going to be focusing on what a glacier is, the different types of glaciers in the world, then a little bit about how glaciers work. We'll talk about kind of how glaciers grow, how they shrink, and a little bit about glacial hydrology. So that's the plan for today. Buckle up. That's what we're going to be looking at. We're going to be looking at these beautiful features right here, glaciers. So here's an example of an alpine glacier from behind me here in the Tetons. So that's the plan for today. I've been thinking, what are you missing that you might find in in my geomorphology class if you would actually have this in person? And I remembered one thing that you haven't seen yet that hasn't made an appearance. It makes an appearance in every single lecture in geomorphology. It is my black coffee cup. So here it is, my black thermos. So I brought it out today so you can get the full Whitman geomorphology lecture experience. So I'm going to have a sip of the coffee. Okay, so now we're ready. We can dive right in and get started on glaciers. First thing I want to mention is that when we think about glacier and glacier processes, there is plenty of evidence for glaciers throughout the world in places where we don't necessarily see glaciers today. And so that can be really broadly distributed. What I mean by that, in the Pacific Northwest, in Seattle, we know that there were glaciers that used to be in Seattle based on the Quaternary sediments that we find in the Puget Lowlands. If we look kind of and take a more geologic timescale, we can actually look at rocks. So here are rocks that also have glacial characteristics. So this is what happens when you have glacial sediment that is lithified into a rock, and we create what's called a tillite. So this is a tillite from South Africa. And so South Africa, not a place you think about glaciers currently. It's actually quite warm. However, during the Carboniferous, over 250 million years ago, this was a time when South Africa was glaciated. And these rocks, these tillites, are evidence of that glaciation. So if we kind of, oh, I know why this isn't working. It's plugged in. Now my slides will advance, hopefully. Okay, so if we look at what the world looked like in the early Permian here, which is the closest time I could find, here's a map of the world and where we would see glaciers. And Africa would be down here. So due to plate tectonics, Africa during the Carboniferous period was at a very high latitude in the southern hemisphere, and thus was glaciated. And so glaciers are all around us, even if we don't see them today. The results of glacial processes are all around us. So we see evidence for glaciers everywhere. Here's an eroding tillite. And then here's a much more recent glaciation where we can actually see some glacial grooves. You see these grooves right here where the glaciers had eroded across this landscape and shaped and scalloped out this landscape. So when we think about this more modern glaciation, let's remember that we're talking about the last glacial maximum roughly 21,000 years ago, when we had a large ice sheet over North America, the Laurentide ice sheet over the central and eastern United States and North America, and then the Cordilleran ice sheet over here, right there, over the western North America, and extending out into up into Alaska Peninsula. So last glacial maximum, this is where we see ice around the world. If we zoom in detail, here is the Cordilleran ice sheet that I mentioned. The Cordilleran ice sheet with the Puget Lobe right here that goes down into the Puget Lowlands. And so we've talked about how important that is for understanding mass movement associated with the landscapes of Seattle. Also remember here that on the other side, we had other lobes Here we've got the Columbia lobe, the Purcell lobe, and these lobes would come down off from the main ice sheet, and these would dam river valleys and create large ice dam lakes that would create massive flooding. And we'll talk about those at a later date. So that's our plan for today. Let's take a step back though. What exactly is a glacier? When we use the term glacier, it's not just an ice cube in your freezer. That does not technically count as a glacier. To be a glacier, you must have an accumulation of ice and snow that's thick enough that it actually flows under its own weight. So it's actually flowing under its own weight. When we talk about glaciers, there's three fundamental types of glaciers and then varieties on those. We have what are called valley glaciers. And what valley glaciers are um, basically glacial ice that's confined to a valley, and then so it flows in that confined valley. So we call that a valley glacier. So they flow from high to low elevations, very similar to streams. Next, we have what are called ice sheets. And so ice sheets are essentially huge unconfined glaciers that are greater than 50,000 square kilometers. These are continental in scale. So ice sheets, currently the only ice sheets are Greenland and Antarctica. And finally, we have what are called ice caps. And so ice caps cover a particular part of a landscape, and they end in valley glaciers that flow off the sides. So they kind of completely cover the top of a mountain range and flow off the sides. A great example of an ice cap from the recent geologic past, the last glacial maximum, would be the Yellowstone ice cap that was on top of the Yellowstone Plateau. And of course, there are many variations on these three, and I encourage you to take an entire class in glaciology where you can learn about the subtle differences in glaciers. Okay, to understand glaciers, we have to really think about kind of how water behaves as a substance, how water transitions H2O from a solid to a liquid and a gas. So this is kind of a phase diagram so we can think about when water is solid, liquid, or vapor. And we're going to think about that with respect to the pressure and the temperature on our x-axis. So what we often think about, for most of us in our everyday world, we just think about one atmosphere, which is the atmospheric pressure at sea level. And so at 1 atmosphere at sea level here, what we see is that if we have a temperature of 0 degrees Celsius, we're right on that boundary between having liquid water. If we warm up, we'll have liquid water, and if we freeze, we will end up freezing. Okay, and then what we do is if we increase the temperature on the x-axis here, if we move right at the liquid phase, we move right at 1 atmosphere, we go all the way up, and we end up at 100 degrees, and that's when we transfer from liquid water to water vapor. And so this is the difference. What I just did here would be moving from the liquid phase to the vapor phase. When we do that, we have evaporation. When we go the other way from vapor to liquid, we call that condensation. When we move up here into the liquid phase, as we move to colder temperatures, we end up moving from liquid to solid water. We call that freezing. The opposite would be melting. Then one other fun one here that actually does happen in glaciers very commonly, if we have solid ice that goes to the vapor phase, we call that sublimation. And if we go right from the vapor phase to the solid phase, we call that deposition. So this is really important, actually, understanding not only how you change the phases of H2O at 1 atmosphere at sea level, but at pressure, because we're going to see some pretty extreme pressures associated with glaciers. And that's really important because as we see, we can do something called pressure melting, where we can have cold frozen ice and we ramp up that pressure, we crank up that pressure, and we can move into the liquid phase at temperatures below 0 degrees. So that's going to be really important. Put that in your brain and remember it as we come to more advanced topics in glaciers. That's called pressure melting. So that'll be really important. Okay, moving on then. Let's talk about the different types of glaciers we see around the world. First is that alpine glacier. When we're talking about kind of valley glaciers, let's look into a little bit more detail about the types of valley glaciers. We're going to see the valley glaciers down here, but one thing I want to mention first is a specific type of glacier that we call a cirque glacier. So here's my picture right here of a cirque glacier. This is a cirque glacier. Cirque glaciers are kind of also known as, I've got it right here, wall glaciers or niche glaciers. They're basically perched high up in an alpine environment. So that's a cirque glacier. Here's another picture of one right here. So there's a cirque glacier as well. And these can be really, really impressive erosional features in alpine environments, erosional mechanisms, I should say. So when you have very, very steep walls where you've eroded back steep sides and you form arêtes and horns, often that glacial erosion is done by these cirque glaciers. So these are high up in the landscape. And what's going to be really important with cirque glaciers is they have this tendency to over erode right at the base of the slope. And so you end up with what is called an over deepening. So cirque glaciers, when they melt away, you'll often end up with a lake that takes its place because you've got this over deepening. So that's a cirque glacier. What extends out from the cirque glacier, if it goes down valley, would be what's called a valley glacier. So as we move down from the alpine landscape, from the high alpine, the lower, we end up with valley glaciers. And here's some beautiful pictures of some valley glaciers. So look right here. There we go. Beautiful valley glacier coming down. Confined flow. We can see streaks in this glacier of sediment that's moving down. So we get that idea that the glacier is flowing and transporting sediment as it moves down valley. Here's a nice aerial photo of some valley glaciers here, a couple valley glaciers, but also some really nice cirque glaciers here. We also got what is evidence for more advanced glaciations in the past. Everyone see this right here. This is a moraine. We'll talk about these in our next lecture. That's great evidence of when these glaciers were larger. So we've got these cirque glaciers and these valley glaciers. Okay, and I have to throw it in because it's a weird one, but it's one of my favorites. So write it down with big hearts next to it. Lyman's favorite type of glacier. That's right. It's a Piedmont glacier. So Piedmont glaciers are valley glaciers that are confined, that then flow out of the terminus of the valley into an unconfined location. And as they do that, they spill out. They look like a Piedmont. We've talked about Piedmonts, these low gradient surfaces. So a Piedmont glacier kind of spills out because it goes from being confined to unconfined. So there's a Piedmont glacier. Okay, here's some pictures of those other types. Here's an ice cap where we have almost the entire top high elevation landscape covered in ice, and then you flow out in confined valley glaciers. So here you can have ice that flows across divides because the ice is higher in elevation than the divide, but then it flows out into confined valley glaciers. So that would be ice cap. Another term we use is this ice field at high elevation. Picture right here is a great example of this ice field and then a valley glacier. Another variant of valley glaciers would be what we call a tidewater glacier. So here's a tidewater glacier that's flowing from down this direction and flows out into the ocean. And so the glacier actually extends out into the ocean. And so we call that a tidewater glacier. Okay, those largest ice forms are what we call ice sheets. So these are at continental scale. They cover the whole continent. So here's an ice sheet. Or, oftentimes associated with ice sheets, if you have significant ice that extends into the ocean, we call that ice shelf. So the largest ice sheet at present is the Antarctic ice sheet. It's over 4 kilometers thick, contains 29 million cubic kilometers of glacial ice. So that's the Antarctic ice sheet picture here. And then the other picture here is the Greenland ice sheet, the other large ice sheet. Here's that Antarctic ice sheet today. Okay. Point right here. As I mentioned, when you get that ice extending off the ice sheet onto the open ocean, we call that an ice shelf. And here's the Ross ice shelf. Okay, just kind of a zoom in here on the ice shelf, and then we see the open ocean off to the side here. And then we've got sea ice kind of broken off from the ice shelf. Okay, let's talk a little bit about how we actually make glaciers. Because what we start with is snow. You start with snow, and then eventually that snow changes into glacial ice. We call that snow metamorphism. And what generally happens during snow metamorphism is you take your beautiful, every snowflake is right individual and beautiful. You take that and you metamorphose it into essentially a big ice grain. So you start with your beautiful snowflake here, and we're going to end up with just basically a grain of ice. So that's what's over here. So this is snow metamorphism. Snow metamorphism. The other thing that's really important to understand with snow metamorphism is the changes in the density, that we go from very, very low densities in a snowflake, 0.05, all the way here to, these are grams per cubic centimeter, to all the way to glacial ice, which is going to be about 0.9 grams per centimeter. So as we move from a snowflake to kind of these rounded off grains, we call this firn. That's snow that's been started to metamorphose. We get these rounded grains, then that transitions to glacial ice. So this takes, we're on the order of moving from a snowflake to full glacier ice, hundreds of years maybe to do that, especially for the really, really large grain. Okay, let's look at some graphs from your textbook looking at snow metamorphism here. If we look at the grains over time, we start with kind of large grains, and then we transition to firn, they get smaller. Then as they grow as ice crystals, they get larger. If we look at the porosity of it, we start with very, very high porosity, and then as we compact and metamorphose that, we decrease the porosity and the density over here. We start with very, very low density and increase that density up to about point. So that's snow hydrology. Here's a nice picture of some decades old glacial ice, and these individual crystals here are about 15 centimeters. Here's what this might look like, kind of if you were able to scratch out and look at the ice in a glacier. So here we've got some foliation in the ice. You can kind of see these elongated parts right here. This is a foliation. And then these pebbles are where there was pebbles in the ice, and the pebbles are warm when the sun hits it and they melt out. Okay, let's move on to how glaciers move. So if we think about the movement of glaciers, we're going to think about this very similar to the way we thought about the debris flows. Remember, with debris flows, we were thinking about how that material moves with respect to stress and strain. So the stress is the force applied to the material, and the strain is how much it deforms. So remember, we talked about Newtonian fluids. So a Newtonian fluid, so that you have a linear relationship between stress and strain, that as you push on the material, it deforms at a rate that's linearly proportional to the stress. We talked about a perfectly plastic material, kind of like Silla putty, that at first there's no, you really can't move it at all, but then once you hit that point where it deforms all at once, then you get a high strain at a very low stress. And so a material that is perfectly plastic would basically have a yield strength. And then when you hit that strength, then the material deforms and strains a lot. So that would be a perfect plastic. Ice behaves by what we call Glen's law. And so Glen's law, we see very, very little strain at low stresses, but it's a nonlinear relationship that when we get to very high stresses, we end up with very, very high strain rates, and that ice can really start deforming significantly. Okay, here's the same material that's in your textbook, so I don't want you to be confused if it looked opposite. Basically, in the textbook, they present this with the axes flipped. So they've got shear stress on the x-axis and strain rate on the y-axis. But this is the same thing here with our linear relationship with the Newtonian fluid, and then our Glen's law here, that with a little bit of stress, there's very little change in the strain. But then as we really ramp up that stress, we end up with very, very high strain. Okay. When we think about the velocity and the deformation of ice in a glacier, going from the top of the glacier to the bottom, because the bottom of the glacier is on bedrock, which is not moving, we have friction at the base, and so we have low velocity at the base of the glacier, and then an increase in the velocity towards the surface. What we see is, because of this change in velocity, is we get significant deformation along the base, little deformation along the surface, which is just kind of long. Okay. Oftentimes with at the base of the glacier, what we have is what's called slide, where the actual entire glacier mass is sliding along on the base of the bedrock. So that would be a portion of the velocity. And then on top of that would be the deformation internally in the ice that we call flow or creep. So the slide is the whole thing moving as it slides along the bedrock. Then we get that flow, the internal deformation of the ice as well. Okay, how that glacier actually slides is going to be really important depending on a couple of characteristics. We're going to look here at a cold base glacier, a warm base glacier, and then a warm base glacier on sediment. So warm and cold on rock, warm on sediment. So a cold base glacier is a glacier where the glacier is actually frozen to the bedrock. And so it's stuck at the bedrock, it doesn't move. That would be a cold base glacier where there's zero slide, and then all of our movement is associated with deformation via flow. So again, with this, we're going to have our velocity at zero at the base and then an increase exponentially as we move up into the flow with the fastest flow at the top. As we move to a warm base glacier, now we're going to see that slide along the base right here. So the whole glacier is sliding along, but then as it's sliding along, because we have so much mass, it's actually deforming as well. And so it's going to be moving much faster, our warm base versus our cold base glacier. Okay, then another really confusing one. How do I want to do this? Am I confusing myself? Okay, there we go. I can't see myself, sorry. Okay, our last one here is the warm base glacier on Till. And this is a little bit more confusing here because what happens is you end up with essentially a frozen portion of the till at the base, and then what's basically what we call fluidized till above that, that's actually sliding along and deforming with the glacier. And then so we have movement of the till and the glacier at the base, and then we end up with deformation in the glacier as well. Cold-based and two examples of warm-based. We see that the velocity of glaciers changes seasonally. So we get changes here. And there's lots of things that can change kind of what happens. Changes in, we'll introduce these terms, ablation zone. Basically, if you end up with lots and lots of snow coming in the winter, maybe that thing's going to flow a lot more associated with that increase in material coming in. So that would be seasonal variations in the glacier speed. Then we also have what are called surges. And so surges are these sudden jerky movements where all of a sudden the glacier starts moving really quickly all at once. And these can last anywhere from hours to days to maybe a couple of weeks. So here's a case of that. This is the variegated glacier in Alaska that had a very fast surge in 1982-83, where it was actually moving at 60 meters per day. So that's the variation glacier speed time. I also want to point out another important fact here with glaciers is that glaciers transport sediment in them as well. So glaciers are going to pick up material in that accumulation zone and then move it, and then that material is going to be melting out in the ablation zone. So sediment is transported along in glaciers, and we'll talk in our next lecture about the types of landforms and sediments that are deposited associated with glaciers. So with the material that gets accumulated in the glacier, if it's on top of the glacier, we call that superglacial. If it's getting moved in with the glacial ice, we call that subglacial. And then as it melts out here, we call this the end glacial. And if it's subglacial, it's just kind of moving out the bottom here, or superglacial moving out the top. Okay, so I've introduced some new terms that are really, really important here. The difference between the ablation zone and the accumulation zone. Every glacier has this boundary between the two, between accumulation and an ablation. And what this means, the accumulation zone is you have net mass increase into the glacier. And then in the ablation zone, you have net loss out of the glacier. So material comes in and then material comes out the bottom via melting. Generally on a glacier, we call if we look at the area, the accumulation area is about 65% of the area of surface of the glacier, meaning that 35% would be the ablation. So ablation area here about 35%, accumulation area about 65%. Okay, that boundary, between the two, between the zone of accumulation at the top of the glacier, the zone of ablation at the bottom of the glacier, right here, we call that the ELA, that boundary between that. This is where you have exactly the net, same amount of material coming in and same amount of material leaving the glacier. That's called the ELA, the equilibrium line altitude. Write that down, ELA, equilibrium line altitude. Above that, we have the accumulation zone. Below that, we have the ablation. Okay, so if we think about ELAs, if we have a warming and we have or less precipitation, the glacier is going to get smaller. So our ELA will go up in elevation. Let's look at this in a little bit more detail. Here's a nice graph from your textbook here, looking at the difference here. So in the accumulation zone, we add mass into the glacier. We get wind and snow that's being blown onto the glacier. We get a little snowfall on the glacier. Maybe we'll get a little bit of sublimation or evaporation. As ice flows into the ablation area, then we get meltwater and we get water melting out the bottom of the glacier. So the blue lines here, mass in, red lines, mass out. If we look here at this net mass, this is our accumulation rate on a glacier. And up here in the accumulation zone, at high elevation, we have the most accumulation, and we're adding mass to the glacier. And then we hit the ELA, where we have a perfect balance between loss and accumulation. Then below that, in the ablation zone, we have that loss, the fastest loss of. So the zone of ablation, melting exceeds accumulation. Zone of accumulation, accumulation exceeds melting. If we think about a glacier in time, if we have the same amount of material coming into the glacier in the zone of accumulation as the amount of material coming out, right here in the zone of wastage, then that glacier is going to stay in place, and we call this a stationary glacier. Stationary glacier, where we have a balance of mass coming in and mass going out. If for some reason we end up adding more snow to the glacier, so if we add more snow to the glacier and we end up accumulating more than we're melting out the base of this thing. So here's the base of it right here. We're getting less wastage. Then our ELA is going to march down valley. It's going to march down valley. The ELA is going to be lower in elevation. So that would make what's called an advancing glacier when accumulation is greater than wastage. We can go the other way too. Let's say that we get less snow on our glacier, and so now because of that, we have more mass coming out the bottom of this thing. And in this case, instead of marching down, our glacier is actually receding. Tall and tan and young and lovely. Okay, so yeah, let's move ahead now with the case of the an example of this accumulation versus wastage and movement of ELAs. So the example here, this is the South Cascade Glacier in Washington State, and we're looking at loss of glacial ice here from 1979 to 2003, or when we have pictures right here, and we're seeing the retreat of that glacier. We've actually been documenting here since 1955 loss of glacial ice, and so here we're looking at glaciers that are receding over time. And worldwide, about 25% of sea level rise has been caused by melting valley glaciers associated, of course, with climate change and warming temperature. Okay, let's finish up by talking a little bit about glacial hydrology. So this is a really important concept for understanding how glaciers move and flow, and that's the movement of water on a glacier. So here's what's called a moulin. This is where basically we have a supraglacial river that's flowing down into the of the glacier. When we're talking about glaciers, another really important point is thinking about that difference between the warm-based and the cold-based glacier again. It's important in thinking about water on that. In a cold-based glacier, what we see is that we've got very, very cold temperatures at the surface, but then as we look at the surface profile, the temperature profile, as we go down into the ice, we end up with cold cold temperatures that don't ever actually, temperatures. Oh, how am I going to explain this? Sorry about this. Um, uh, as we move down into the ice, we see the temperatures warm up. Temperatures warm up because we've got bedrock down here that has internal heat coming up from the earth. So, because of that, we see warmer temperatures at the base of the glacier. Now, interestingly, we can look at that pressure melting curve. Remember back to the beginning of the lecture, I mentioned that this is important, that because of the thicker ice at the base of the glacier, you don't need to necessarily be uh, above freezing to get the ice to melt. And so if these don't cross, then you'll have what's called a cold base glacier. But look at this example here. Here we have a warmer glacier, and in this case, as that ice gets warmer beneath the surface, it actually meets the pressure melting curve. And because of that, you end up with water at the base of the glacier. And we call this a warm base glacier, where you can have water at the base of the glacier. And that is going to change the hydrology and the movement of the glacier, because this is more likely to slide than the glacier, the cold base glacier, which is frozen to the bed. Our other picture here is from Greenland, showing the portions of the glacier that are warm base versus cold base. Because of this heat that is coming in from the Earth's surface, we actually end up in pressure melting. We end up with an incredible system of lakes and essentially rivers that are beneath the Antarctic ice sheet. So this is just showing these lakes and rivers that actually connected beneath the Antarctic ice sheet. That's pretty cool. Okay, let's look at a couple ice structures here when we're looking at our ice as well. With glaciers, we see stratification, and so that's from the yearly snow events. So you can kind of track from the most recent snow to much older snow as we go down. So that's ice stratification. As those stratified layers start to deform, we can create what are called foliations, which are these deformation of layers within the glacier. As glaciers deform, they'll crack open as well, and then you can create what's called a crevasse. So a crevasse is an opening in the glacier that can extend down for, tens to maybe even hundreds of meters. That's what, mountaineers fall in if they're careful. Here's a spectacular picture of foliation with glacial ice, because you've got that internal deformation. Okay, and finally, we'll leave you with Lyman's favorite ice feature. So I've already told you about my favorite type of glacier, the Piedmont Glacier. Here's my favorite ice feature, the Bergschrund. So the Bergschrund here is where a cirque glacier detaches from the valley wall and you actually get a gap. So that's the Bergschrund right here. I've got a fun story to tell you about the Bergschrund in class, so don't forget to ask me, Lyman, what's the story about the Bergschrund Glacier? Not glacier, the Bergschrund, and we'll let you know. So that's all I've got for you today. Great job. We're cruising along in glaciers now. Next, when you come back and learn about glaciers, we'll be talking about glacial erosion and glacial deposition. So have a great day, and we'll see you soon. Bye.
We'll stand on board his brother. We'll rule the sea, just you and me. Let the devil take another.